So I always thought Dalton's law was kind of silly. It really just states the obvious. So these capital P's stand for partial pressures, and it's specific to the pressure of the gas indicated by the subscript. So if you add up the pressures of all of these individual gases, maybe in the room or in your beaker or system or whatnot, then that's going to equal the total pressure in the room. So the sum of the parts equals the whole. Nothing too mind-blowing there. There are cool applications to the law though, and one of them involves combining this idea of partial pressure with mole fractions. So you can calculate the partial pressure of any individual gas if you know its mole fraction and you multiply by the total pressure. Let's see some applications. So in the first problem, they told us that we have 0.197 moles of carbon dioxide and 0.00278 moles of water vapor. So what I went ahead and did is I calculated the mole fraction with respect to carbon dioxide. So the moles of carbon dioxide are in the numerator and the total moles are in the denominator. I got 0.986. It's super helpful to remember that with your mole fractions, if you have a binary system and you add up the two mole fractions, they need to equal 1. Or if there's 3 things in your system, then if you add up all 3 mole fractions, it needs to equal 1, and so on. So I took advantage of that just to maybe make things a little bit quicker, and I did 1 minus my previous answer, and that got me the mole fraction of water. I had the whole value in my calculator. That's why it doesn't exactly add up to 1 here. Alright, so with that, and to be perfectly honest, sometimes I verify that number. I go ahead and independently calculate the mole fraction of water and make sure it matches, because I'm always paranoid that I plugged in something wrong. So many different ways that you can get at the answer. Alrighty, so you can start the second part of this problem by either calculating the partial pressure of the carbon dioxide or the partial pressure of the water, whatever you want to do. I chose carbon dioxide. So we're going to plug in our total pressure, which was given to us, 2.50 atmospheres. This is kind of just extra information. And we're going to multiply by the mole fraction of the carbon dioxide, which is 0.986. And when I did that, I got a partial pressure for my carbon dioxide of 2.465 ATMs. Now, again, there's so many different ways to approach this. You could do the same thing. You could say the partial pressure of the water equals the total pressure times the mole fraction of the water. And actually, that would be the reason why I calculated that value down there. The other thing you can do is you could take advantage of Dalton's law of partial pressures. And I honestly did it both ways. Again, I just always want to check. Since the system only has 2 gases, the carbon dioxide and the water, they need to add up to the 2.50. So we can say the partial pressure of the carbon dioxide plus the partial pressure of the water should equal 2.50. So if we do 2.50 minus our previous answer, the 2.465 ATMs, then we get 0.0348 ATMs, which will be our partial pressure of our water vapor. Again, now that I'm looking at this, I did calculate it both ways, and that's how I used this value. Just to verify my answer, I did the partial pressure of the water equals the total pressure, which is 2.50 ATMs, times 0.0139, the mole fraction. And the mole fractions are unitless, right? And that's important here because the only units we want are atmospheres. When I did that, I got 0.00278 0.3475 ATMs. So the same difference, if I round to the 3 sig figs, kind of just verified my answer over there. This problem here is another great example of how to use Dalton's law of partial pressures. So we're given the mass of two different gases, which I went ahead and used their respective molar masses to convert both masses to grams. We're also told that the total volume of the container is equal to 100 liters, and we're given a temperature. So the ideal gas law, PV equals nRT, can be rewritten to be specific to a particular element or gas. So we could do the partial pressure of A times the volume of A equals moles of A. I want to put a subscript on R because it's a constant. And then typically the temperature of the system is going to apply to all the gases. But if not, then you could put a subscript on temperature as well. So we can take this and rewrite it then to say total pressure times total volume equals total moles times R times T. This is awesome because this is going to allow me to solve for the total pressure in my system, and along with the mole fraction of the hydrogen gas, which I went ahead and already calculated, I can get the partial pressure of the hydrogen gas and then the argon gas as well. So I went ahead and after converting both masses to their individual moles, I added the two mole values up to get a total moles. So that's going to come in really handy right here. So let's start plugging and chugging. Total pressure is going to equal those total moles, 7.9484 moles times R times temperature. It better be in Kelvin, and it is 290 Kelvin. And I want to divide the whole thing by the total volume, which is 100 liters. Let's see how the units are canceling and what we wind up with. So moles canceling with moles, volume with liters, Kelvin with Kelvin, and I'm just left with atmospheres. So perfect. When I did that earlier, I got a total pressure of 1.8915 atmospheres. At this point, I can take that value and use the relationship with partial pressure. So we know that the partial pressure of hydrogen gas is going to equal the total pressure times the mole fraction of hydrogen gas. So I'm going to do 1.8915 ATMs times the unitless mole fraction, which is really important, it's unitless. And that gives me 1.67 ATMs as my partial pressure for my hydrogen gas. So there's two ways to go about calculating the partial pressure of the argon. You can use this relationship again, except do partial pressure of argon equals total pressure times the mole fraction of argon. Perfectly acceptable. Since it's about Dalton's law of partial pressures, I'm going to take advantage of that relationship, which tells us that the partial pressure of the hydrogen gas plus the partial pressure of the argon gas needs to be equal to the total pressure in the system. So hydrogen we know is 1.67 ATMs. We don't know the argon quite yet, and we know the total pressure is 1.8915 ATMs. And so when we solve and subtract over, we get a partial pressure for the argon equal to 0.219 atms.